Today we want to derive a Lorentz transformation. It will be a special case of this transformation. For the situation, we have two inertial frames of reference, the first and the second. And we assume that the second frame of reference is moving with a constant speed v in the direction of the axis x. The more general Lorentz transformation is for the case when this velocity has components in the direction of all axes. I should remind you about Galileo transformation. We know that this transformation is not true because it does not comply with main postulates of special theory of relativity. I mean that velocity, the speed of light is the same in all inertial frames of reference, and that nothing can move faster than light. Lorentz transformation comply with these main postulates of special theory of relativity. So let's do it. Galileo transformation is not true, but it let us foresee the form of the real transformation. Galileo transformation is not true, but it helps us to foresee the form of the real transformation. We see that spatial coordinate x dash depends on x and t linearly. We expect that the same will be in the real Lorentz transformation. And we know that Lorentz transformation for velocities much slower than the speed of light should give us Galileo transformation. So we foresee the form of the real transformation. We see that x dash depends on x and t linearly. A and b are just constants, and we should calculate these constants. It will be easy to calculate the constant b. Let's assume that for the t equal to 0, both beginnings of these two frames will be in the same place. So this point will be here. And let's assume that some event happens in the beginning of the second frame of reference. So x dash for this event is equal to 0. And x is equal v times t because this point is moving in the direction of the axis x with the speed v. Now we'll just put these values to the equations above, and it's done here. And we can calculate from this equation the constant p. Then we just put this value here, and we could write it in this form. If you want to find inverse transformation, then we just put in the place, we just change x dash to x to x dash, t to t dash, and v to minus v. We should understand that v in this equation is not the value of velocity. It is a coordinate of velocity vector. I should remind that if a vector is parallel to the axis, then coordinate of the vector is equal to value of this vector if this vector is directed the same as the axis, but is equal to minus value of vector if the vector is opposite to the axis. Now we want to calculate the constant a. How to do it? Let's assume once more that for the t equal to 0, beginnings of all of these two frames of reference are in the same place, and we send a beam of light from this point and also from this point in the direction of the axis x and of course x dash. Then we could write that x is equal c times t and x dash is equal c times t dash. It is because velocity, speed of light in all inertial frames of reference is the same, is equal to c. Then it's enough to put these values x and x dash to these two equations. So here we just put c times t dash. Here we put c times t. Here we put c times t, and here we put c times t dash. We can change form of these equations to such, and we change the sides of the second equation. It's done here, and we divide left sides of these two equations and then right sides of these equations. We achieve such equation. Now we can transform this equation and calculate the value of constant a. And it's done here. Now we put this constant to both these equations, and we have and then we would have transformations of coordinate x and x dash, and it is on the second table. So now we'll put the value of constant a to both of these equations, like I've done it here, and that's a Lorentz transformation for coordinate x and inverse transformation. Now we only have to find the transformation of time. We will use these two equations, and from this inverse transformation we'll calculate x dash, and it's done here, and we put this value, right side of this equation, to this place. And it's done here. Now we change sign of this expression and multiply both sides of this equation by the square root of 1 minus v squared by c squared. If we multiply this root by this root, just the root will vanish, and we'll achieve 1 minus has v squared by c squared multiplied by x. And we have it here. And if we multiply this by this root will vanish. And if we multiply this expression by this root, we will have such expression. Now we see that we can get rid of x, and if we divide both sides of this equation by v, we achieve such equation. Now it's enough to transform this equation and calculate t dash from it. But it's done here we calculated t dash from the previous equation, and to find inverse transformation, we just change in this equation t dash to t to t dash, x to x dash, and v to minus v. We should understand what is v in this equation. It is not value of velocity. It is coordinate of velocity vector, and it is expressed by such equation. Delta x can be greater than 0 if second frame of reference is moving in the same direction as the axis x, and delta x is less than 0 if second frame of reference is moving opposite to the axis x. And we know that first frame of reference is moving in this direction related to the second frame of reference. So coordinate of velocity v is less than 0. So here instead of v we put minus v, and we have inverse transformation. Now we can write all this transformation in one place. We should remember that there is no movement in the direction of axis y and z, so these coordinates don't change. And the problem we try to solve, we've solved. So it's the end of this lesson. Next lesson about special relativity. Today we want to solve a problem of adding velocities in special relativity. Let's assume that we have two inertial frames of reference, the first and the second, and the second frame of reference is moving with constant speed in the direction of the axis x related to the first frame of reference. We have here an object moving also in the direction of the axis x, and the velocity of this object will be measured by these two observers from the first frame of reference and the second frame of reference. We write here equations for U. It is velocity of this object measured by the first observer. It's equal to delta x divided by delta t. Both values are measured in this frame of reference, and U dash will be velocity of this object measured in the second frame of reference. It's equal delta x dash divided by delta t dash. We'll will transform this second equation to such form, delta x dash equals u dash times delta t dash. We want to know what value of the velocity of this object will be measured by the observer in the first frame of reference if observer in the second frame of reference achieved value u dash. If we believed in Galileo transformations, the answer for this question would be very simple. Velocity of this object measured in the first frame of reference would be just velocity measured in the second frame of reference plus v. We know that this equation is not true. It's really easy to prove. Let's assume that this object is just light, and velocity of light is just in the vacuum is just c. So if we put here c, then the speed of light measured in the first frame of reference would be c plus v. It would be greater than the speed of light in the vacuum, and we know that nothing can move faster than light in the vacuum, and the speed of light in all inertial frames of reference is the same and equals c. So we can't use this transformation. We should use transformation which complies with main postulates of special theory of relativity. This transformation is called Lorentz transformation. I wrote here two equations describing this transformation, but it is a special case of Lorentz transformation. Just the situation, these equations describe such a situation where second frame of reference is moving with constant speed and in the direction of the axis x. From these two equations, we can compute delta x dash and delta t dash. As you can see, these equations are very similar. It is because x dash and t dash depend on x and t linearly. So instead of x dash in this equation, we will have delta x dash. Instead of x, we will have delta x, and instead of t, we will have delta t in both. Now we have four equations: 1, 2, 3, 4. The only thing we have to do now is just combine these four equations, and it can be done in various ways. I put here the right side of this equation. It's not here. Then I put here the right side of this equation. It's here. Now we see that on both sides we have the same denominator. So if we will multiply both sides by the square root of 1 minus v squared by c squared, then these denominators will vanish. Next, we divide both sides of this equation by delta t, and we have it here. Delta t divided by delta t is just 1. Delta t divided by delta t is just 1. Delta x divided by delta t, it's u. It is a velocity of this object measured in the first frame of reference. And the same is here. So we have this equation. And now we almost solved our problem. It's enough to transform this equation and calculate from it velocity U, velocity measured in the first frame of reference, and it's done here, or calculate from this equation velocity U dash, velocity measure of this object measured in the second frame of reference, and it's made here. The only thing we should do now is to prove that these equations comply with main postulates of the special theory of relativity. I mean that speed of light in the vacuum is the same in all the inertial frames of reference, and that there is nothing can move faster than light. It is easy to prove. Let's assume that our object is just light. So U dash is equal C. Now we put C to this equation here and here, and it's down here. Now we have such equation. We change the form to this, and we see that the result is U equals C. So the speed of light in both these inertial frames of reference is the same and is equal the speed of light in the vacuum. So now we solved this problem. So it's